Okay, so welcome back to the second talk this afternoon. And it's a great pleasure to have Vida Dujmović, who's going to talk on product structure theory with applications.
Thank you, Alex. Thank you, Christina, for inviting me. It's my pleasure to be part of this seminar series. Of course, I wish we are in all together, but hopefully next year, one that comes after. So I'm going to talk about product structure theorem, let's say, or rather its application. I'm just going to state the theorem. It's, that's the next slide. I'm just going to state the theorem because what I want to talk about is how you can use it, possibly for some problems that you have been stuck in. At least for us, a group of people who have been working on this, it unstuck us from a number of problems we were working on in the past. So I'm going to start with listing applications that we worked on and applied and solved problems in using this structure theory. For example, the first one that we did is we resolved almost 30-year-old open problem on queue layouts of graphs using this product structure theory. Also about 20-year-old problem on non-repetitive colorings. Then there are results by other authors on P-centered colorings, universal graphs, cluster colorings, and so on. So what my goal is today is to show you two applications. One is an easy one, so you can see how typically you would use this product structure theorem to get a new result. Another one is not so easy one. And I will try to give you an idea why is it more difficult than the others. Well, actually, it's going to be obvious why is it more difficult than the others. And one of the nice things about this product structure theory that it really typically gives super simple proofs once you know of this theorem, and it gives a better bound. In case of, for example, queue layout, wrong thing. Okay, so in the case of queue layouts, for example, the previous best bound was log n, so it depended on number of vertices of the graph, and we got a constant using product structure theorem. The same was the case for non-repetitive graph colorings. For P-centered colorings, the previous best bound was about P to the 19 or 17, so they reduced it to P to the 3 using product structure theory, and so on. Okay, so let me tell you what the theorem says and for what classes of graphs, it's applicable. For that, I need to define a strong product of graphs, of two graphs. So what's a strong product of two graphs? If you have a graph H, like this one here, and a graph P, in this case, is a path, strong product of these two graphs, you're going to take a Cartesian product of the vertices of the graph. So every two vertices in one vertex from P, one vertex from H is going to create a result in a vertex in H times P. So what about the edges? The way you get an edge is for any edge in graph P, and let's say any edge in graph H, so let's look at this one and this one, there are endpoints defined for vertices in the product, okay? So what you do basically is you add all the possible edges between these four vertices. So for every pair of edges, one from P, one from H, you look at the corresponding four vertices in the product and add all the possible edges between those four vertices. This is how strong product is defined. You may be familiar with, probably you are, with the Cartesian product. In that case, the definition is the same, except that you don't add the crosses. The only edges you add are these four edges and not the cross edges. Okay, so we are working with a strong product of two graphs. And the theorem that we proved, by we, I mean myself, Gwen, Jorette, Piotr Micek, Pat Mooring, Torsten Urquhart, and David Wood. By the way, you can see, as usual, that these are somebody else's slides. If they are handwritten, those that are handwritten are mine. So let me give a credit to people who made these slides. Some of them are mine, only the handwritten one. The rest of them are somebody else. I think this particular one is by David. That's why I had to add the rest of his letters here on on the theorem. So what the theorem says, let's go back to that. It says that every planar, so in this talk, I'm going to talk about planar graphs, but this type of similar theorem to this exists for bounded genus graph, and in fact, more generally, all apex minor free graphs. It doesn't matter if you don't know what that is. I'm going to only be talking about planar graphs in this talk. All right, so it says that every planar graph is a subgraph of a product of two graphs, strong product of two graphs, H and P is indeed a path, okay, so a path like this, and H is a graph of small 3-bit, in fact, 3-bit at most 8. It doesn't matter, I'm really not going to use any properties of 3-bit in this graph. If you know what 3-bit is, great. If you don't, it really doesn't matter. So the only thing that you're going to see that I use for 3-bit, so that many of these problems, in fact, absolutely all of these problems from these applications, everything was known, the tight bounds were known. Oh, I'm lying, not this one. The tight bounds, except for this vertex ranking, the tight bounds were already known for the graph of constant 3-bit, okay? So what we have here is that, oh, sorry, I'm getting distracted by reading the questions. I guess I shouldn't be doing that. What we have here is that planar graphs are products of a path and a graph of 3-bit at most 8. So they're a subgraph of such a graph. Okay, so how would you use this? Again, I'm not going to find 3-bit, but there is in my slides some sort of a definition if you would like to, if you looked at it before. So let's figure out what is this good for. So hopefully now that this structure seems to be somehow something that we can have handle on, it doesn't look completely wild. So hopefully if you're trying to prove some bound on planar graphs and you know a bound for bounded 3-bit graphs, you know how to solve a problem on bounded 3-bit graphs, and you know how to solve the problem on a path, let's try to use this to put it together. That's the main idea. And typically, other than this second example, I'll show you application is actually super easy. So let me start with a new application that we have that is also very easy. Okay, so we're gonna look at the particular, this one, vertex ranking. So I'm gonna start by telling you how to apply this structure theorem of planar graph, product structure theorem of planar graph on a problem on so-called vertex ranking. So first of all, what is vertex ranking? It's a type of a graph coloring, okay? In particular, it's called L vertex ranking. So what is it? So basically, we color the vertices of graph G. We assign it integers, let's say positive integers. These are the colors. So we assign colors to the vertices, and two things have to be satisfied. One is either, so the two things that have to be satisfied is that for every path, non-trivial, so path of length P, where P is at least 1, and for me, length is the number of edges in the path, okay? So if you have two vertices and one edge in between, that's the path of length 1. Okay, so if you look at the non-trivial paths, so path of at least length 1, the following two properties have to be satisfied. First of all, either the endpoints of the path have distinct colors. So here's the path here, and it has distinct colors. Then we don't have to worry about anything else, okay? Or if the endpoints have the same color, then what is required is that on that path, there is a vertex with a bigger color, okay? That in fact implies that there is a vertex with a unique color that is also a higher color. It's not difficult to see that. So in other words, we can say that if the endpoints have the same color, the maximum, there is a maximum color on that path that is unique, okay? So we see this on this example. So what type of coloring is this? What we want, actually, the part that I missed, is that this is true. There is a parameter L on every path of length 2. Every path of length L. So every path of length L, you say we have a vertex L coloring if these two properties are satisfied. First thing to notice is that this is a proper coloring. Well, L needs to be at least 1. Okay, so this is a proper coloring because, for example, I mean, this is a path, and if you give them the same color, well, then you are breaking this thing. There is no vertex here with a bigger color than its endpoints. It has to be a strictly bigger color than the endpoints. Okay, so it's a proper coloring. It's also star coloring, meaning between two color classes, you cannot have a path of length at least 4, because the colors will be, let's say, 1, 2, 1, 2, 1, 2, if it's 2 colorable. But then this part here breaks the rule for L is 2. So in paths of length 2, we have here that endpoints have color 2. But there is no vertex on the path that has higher color than 2. Okay, so it's proper coloring, it's star coloring, and so on. This type of coloring has been studied quite a lot for when L is an infinity, you get so-called vertex ranking coloring as well. Okay, so our goal is, let's see what was known about this type of coloring. Let's say for trees, for example, recently in 2015, here's the results that were known. There was a tight bound was known for trees. So basically all the trees have, and here this is for fixed L. This is new for me to be using this. Okay, so for fixed L, so paths of some fixed length L, you can color a tree with at most log n over log n colors. And actually that's best possible. So unlike the other problems I was mentioning, such as queue layouts, non-repetitive colorings, and so on, where the correct answer turned out to be constant, here the correct answer is not constant number of colors. So for trees, we know the correct answer. And what I proved for planar graphs is that the upper bound is log n, and the lower bound, you only know lower bound was also from trees, which is log n over log n. So there was a gap here between, and the question was, what was the correct answer for planar graph? Is it log n, is it log n over log n, or is it something in between? Okay. By the way, I would like here, it says contrast with, in particular this one, there is a coloring called centered coloring that has been studied, or p-centered coloring that has been studied a lot. And in an essence, if you know this p-centered coloring definition, the only difference that it says is that on the path, there is a unique color. It doesn't insist that on any path of length p, that you have, that the unique color is at the same time the maximum color. So the difference is that it has been studied before a lot in this centered coloring, that on each path, that there is a unique color. Each part of length p, there is a unique color. And here, in addition to it being unique, you want to have to be bigger than the colors of the endpoint. And that makes huge difference, because these centered colorings, you can prove a constant bound if p is a constant. And here, this is not the case. It makes a huge difference, this introducing this maximum. By the way, it does have some application that was, Samorodinsky does lots of geometry. It came from some geometric application, this problem, but I forgot what it was. So let me not dwell on that. Okay, so here's our goal. The goal was to solve this problem. So with this product structure theory, we were even thinking, okay, let's go and look for anything that's not known about planar graphs. But this is one of the papers that I knew from before that we didn't know the answer. Okay, so the question is, what's the gap here? What's known? And it turns out the answer is in between. I thought, I just want to show you this as application because I thought it was such an interesting bound. And this is a tight bound. So for every L, at least 2, so parts of the parts of length at least 2, where L is fixed, every n vertex planar graph has this L vertex colorings. Again, L is hidden here because it's considered constant. It has coloring with log n over log, 3 logs n, and this is asymptotically optimal. So basically for infinitely many n's. this turns out to be the correct answer. By the way, this is joint work with Jit Bose, our student Bernouche, and Pat Mooring. This is fairly recent. This is the COVID work. So how we do this? This was actually, the part I'm going to show you is very easy, but okay, so assume you want to solve this problem and assume on planar graphs. All right, so we know that planar graphs are now products on some graph H, and are subgraphs of a product of some graph H and a path, but H has a constant tree width. Okay, so suppose somebody solved this problem on graphs of bounded tree width. That we know how to do this with n over log, whatever we want to know. We know that bound. We want to apply the known bound. So suppose we know how to color this, and we know how to color this. Okay. And we can, one of the nice things for many of these upper bounds, of course, problems is that you can assume that this is all edge maximal, that you really have the full product. If you prove the bound for that, you have the bound for the subgraphs, which is what planar graphs are. They are subgraphs of this. Okay, so what would be, this is one of the first things you would probably try if you ever spend 20 minutes thinking about this. Okay, so let's say L is, I'm gonna take an example where L is 2. Okay, so all I want is that on path of length at most 2, either this has distinct colors, or if these two colors are the same, then this one has to be bigger. Okay, so we have paths of length at most 2. So we know that in this product, they cannot span more than, how do I do it? They cannot span more than, let's say, let's call these layers of vertices of P. They cannot travel more than 2 edges, okay? The path will be contained in there. Okay, so first thing we can try to do is the obvious thing to try to do is to assign 2 colors to vertices of the product. Assign 2 colors, one from coloring of P and the other one from coloring of H, if you know them. Okay, so I'm gonna do exactly that. So I'm gonna take here, given that we know coloring of H, I'm gonna put here whatever color for vertex X comes from H. Or Y comes from H. I'm mixing these up. So this comes from H. That's going to be one color. And the other one, I'm not going to really use vertex ranking. What I'm going to do is I'm going to use distance coloring on this, on the path, meaning that any path of length at most 2, all the vertices have distinct colors. So I'm going to do 1, 2, 3, 1, 2, 3, and so on. That type of coloring I'm going to use as a second color here. So that's going to be coloring, distance coloring. It's not easy. So vertex gets a color, distance coloring. So let me, I guess I wrote it here. So here you get the vertex that comes from H, the Y coordinate of the vertex, gets the coloring from the coloring of bounded tree with graph H. And the second component of the color is a distant coloring of the path. Okay, that's it. And why does this work? We are basically done. The reason this works, so let's look at the path. I'm going to now draw it longer. So this green path, if we look at it, it is going, it can only, because it has length at most 3, it can only span at most 3 layers. I draw that longer here. But what we know is that that path is contained within these 3 layers here. And each vertex, all the vertices in this row, in row 1, got the first color 1. All of them here got the first color 2, and all of them here got the first color 3. Okay, what that means is that if this path, if the endpoints of the path have distinct colors, we are done according to that definition. But if they have the same color, that means that the path started in the same row and ended in the same row. Okay, so that this is what ensures that. And now if we look at this path going through these three layers, well, that corresponds, if we look at a graph induced by this row 3, let me call it row 3, well, that's a graph H, okay? So this path here corresponds to a walk in this graph H. And that means that once you can convert that walk in H into an actual path in H, and which means that on that path, one of the vertices, which is also visited by a walk, has to have a higher color from the coloring of H. Hopefully that makes sense, but it's really super simple idea. You try the first thing and you check if it works. Okay, so you combine the two colors. One is a distance coloring and one is the vertex ranking coloring of bounded tree-width graphs. You put the two together and it works, okay? So all of our examples in bounded queue layouts and everything else, it worked like that. It was really half a page. First idea you try how to combine, once you know how to solve it for the path, how to solve it for the bounded tree-width graph, you get your result. Okay, so what do we get here? What did we conclude here? That because this is a pair of colors, we get, what's the number of colors we get? We get whatever the coloring, number of colors we need for vertex ranking of bounded tree-width graph. That's the bounded tree-width graph from planar graph. And we use distance coloring of the path. Okay, so distance coloring of the path where all the vertices on the path of length at most L get different colors. It's at most L plus 1 color, so that's a constant. So then the question becomes, so what is the vertex L vertex ranking number of bounded tree-width graph? And unlike the other problems that we looked at, the answer was actually not known for this. So actually the whole paper is about that we worked on, was answering the question of what is the correct answer for a bounded tree-width graphs. And it's another strange bound. In fact, let's not get bogged down in details. This is a so-called simple tree-width. Which is, if you're familiar with K-trees, it's a tree, it's K-tree, it comes from K-trees where you're only allowed to add a simplicity vertex to a clique once. You cannot add it more than once. And the simple tree-width appears in a couple of these problems of similar flavor. It turns out the correct bound on graphs of simple tree-width T is log n over t times logs of n. So what did we do in this, in what I've shown you? That, I mean, if we just plug it in, what I just told you, this bound, it would look like our bound is, when I plug it in here, it looks like this gives log n over log 8 times n, rather than 3, which is what I promised. This gives me an excuse to tell you actually a different version of a product structure theorem that we in fact use for this result. And in some cases, it may give you better result than the first one I mentioned, and in fact, optimal result. So one of the things we also proved is that a variant of the product structure theorem, which says that every planar graph is a subgraph, we have a product of 3 graphs this time. So it's not just bounded tree-width graph times a path. We have a bounded tree-width graph times a path times a complete graph on 3 vertices. But this time we know something stronger about H, and that is that H is planar graph and has simple tree-width 3. So when we apply our tree-width result, when we use that theorem to obtain our result here, we would get 3 logs, and that's the one that turns out to be optimal. Okay, so that's all I have about this application. I don't know if you have any questions. Okay, so let me tell you about the second application. So whenever, as I said, whenever you are looking for some upper bounds like this, and it doesn't really matter if you're a subgraph or you take an edge maximal product, it's likely that some simple idea is going to help. But here's a problem where we didn't have a simple idea. I'm going to talk about compact encodings for the second half of this talk, or rather, they are related to universal graphs. Okay, and this is joint work with Louis Esper, Cyril Gawal, Gwen Joret, Piotr Micek, and Pat Morin. So let me define what we're trying to solve. And this one, again, was related to work that goes all the way back to 1988. And there was a problem that kept on staying unsolved from that time. And we managed to solve that problem optimally using product structure theory and many other ingredients. And I'm going to try to give you some flavor. So what is it that you want? You want to label vertices of the graph. And just using the labels, you want to test, if I give you two labels for two vertices, you want to test, you want to say are they adjacent or not. Okay, so what you're looking for is so-called adjacency tester. And what it does is for two binary strings, it outputs either 0 or 1. So 0 for no edge, 1 for there is an edge. And also for a graph G, we say that L is a labeling function of G. If you assign to every vertex of G some binary string. Okay, so when does the labeling work, given some adjacency tester? We say that labeling of a graph works on with this adjacency testing. If you give me any two vertices, and I take two labels of those two vertices and give it to adjacency tester, the adjacency tester tell me yes, 1 if the edge is in the graph, and give me 0 if the edge is not in the graph. So here's example. For example, here, if label is of this vertex is 0, 0, label of this vertex is 1, 0, 0, I want adjacency tester to output 1. And in example like this, the adjacency tester would output 0. So for the labeling, this labeling, the adjacency tester, we would say works. Well, at least it works for these two examples I picked. Okay, so we say that a family of graphs admits f of n. This is the size of the label. Okay, so we're looking at family of graphs with at most n vertices or n vertices. We say that that family, think of planar graphs again, has f of n bit labeling scheme. If we have adjacency tester, such that you give me two labels, you get yes or no. And for each n vertex graph in the family, we have labeling where the lengths of the labels are f of n, such that that adjacency tester works. Okay, so what you want is you want to label the vertices of, you want to come up with a way to label the vertices of a class of graphs or graphs in a family, such that these labels are as short as possible. And yet there is adjacency tester, like one tester, one algorithm that tells you, are these two adjacent? Given just two labels, are the vertices in question adjacent? Okay, so an example that I was just giving you, here's an example. If you look at the 3 cube, which is drawn here in the picture, you can say, here's an example of adjacency tester. You can say you should return 1 if the Hamming distance between two binary strings is 1, otherwise you turn 0. So that's a function, adjacency tester function, and a standard labeling of a cube is a labeling that works with this adjacency tester. So this type of labeling exists for all D cubes. So we can say that the family of D cubes has a log n bit labeling scheme. if you use adjacency, if you use the standard labeling and adjacency tester that does the test for a Hamming distance. Okay, so that's one family of graphs for which we know a nice, concise labeling scheme. So of course, the goal is there is a labeling scheme for any graph family. You can come up with a trivial labeling scheme. You label the vertices of any graph. Let's say this is your algorithm. You label the vertices of any graph with a 1 to n, that's log n bits. And then for each vertex, you append to it a list of all its neighbors. What's that? That can end up with n log n bits. Okay, so what we want is something much more concise and better depending on the family of graphs. Okay. So before I show you, so for example, what can you do with trees? So here's a trivial example of how you can achieve better than that labeling scheme, better than n log n bits labeling scheme for trees. So you label every node in a tree, you root the tree, you label every node of a tree with the log n bits. You give them names 1 to n, and then for each vertex, you just append the label of the parent. Okay, so that's 2 log n, and if you give me 2 vertices, one of them is going to have the other as a parent if they're adjacent, otherwise not. So 2 log n, you can do all the trees with 2 log n bits. Okay, just to give you some less trivial bound for trees at least. Okay, so what does this have to do with the universal graphs? There's a very cute theorem. There used to be here a folklore. Oh, you see, it's folklore because I'm on an eraser, but I erased this. It used to say folklore, but as you can see, I changed it. Apparently, this was in some paper. It became folklore after that. That there is a if and only if relationship between these labeling schemes and induced universal graph for the particular class. So if you can do labeling schemes with f of n bits, then there exists a universal graph. What does that mean? Let me actually define what it means. I don't know if I have that. Okay, so what is a universal? Okay, let's say we are looking for a graph that contain all n vertex planar graphs as an induced graph. Okay, you can say, all right, take all n vertex planar graph, takes a union, that's the one, but that one is a huge graph. So you want as small as possible graph that contains all n vertex planar graphs. Suppose we can label the vertices of planar graph with f of n bits. I claim that there is a universal graph with 2 to the f of n vertices. Okay, so the way you do this is you basically, for every binary string of f of n length, you create a vertex. Those are the vertices of your universal graph. Then you ask adjacency tester for any 2 of these labels, is an edge there? If adjacency tester says edge is there, you put it there. If it says no, you don't. Okay, oh, actually, I think this is where that proof is. Okay, so this is this is the definition of the graph. And then any graph G, you're going to find it there. You read off its label. So I take a planar graph, n vertex planar graph G that is labeled. I'm going to find the corresponding vertices. So it has labels. I found those labeled vertices in a universal graph, and all the edges are exactly there or not as in the planar graph that I'm looking for. Okay, so so what does this imply for trees, for example? We just said that planar graphs have, the trees have labeling scheme with 2 log n bits. So that means there is a universal graph on n square vertices that contains every tree as an induced, every n vertex tree as an induced tree. Okay, so, and this is, by the way, this is if and only if, this relationship between induced universal graphs and the labelings. All right, so the goal is the same. You want as small universal graph for a graph family and as small a length of the labeling for a graph family. Okay. So what was known, as I mentioned, the trivial bound for trees is actually 2 log n, but there was a series of papers improving that. 1 log n plus lower order terms was proved by Chang in 1990. That was further improved until it culminated with this result 3 or 4 years ago now, where basically there's only a plus a constant next to the log. So trees can be done with, and of course this is optimal. I mean, 1 in front of the log n is best you can hope for. So what about plain bounded tree with graphs? That too, so here's where we pay attention. We know now that there is basically optimal result for bounded tree with us. And for me, I call something optimal if you have a 1 in front of log n. For now, we don't worry about lower or improving lower order terms. Okay, so it was known, optimal result up to lower order terms were known for bounded tree with graphs, and it was known for trees. Okay, so what about planar graphs? There was a series of results on planar graphs. The earliest ones are 6 log n. They are based on the fact that planar graphs are 5 degenerate. Then 4 log n that are based on the fact that the edges of planar graphs can be oriented such that there's at most 3 outgoing edges. Then that was 4 log n and so on. Then there was a 2 log n result based on the fact that planar graphs can be, edges of planar graphs can be partitioned into 2 outer planar graphs. And the most recent result, this is from 2020, or was it 2019? Doesn't matter. There was a breakthrough because this 2 here was standing there for many years, since 2007. There was no improvement on 2 for planar graphs. So there was a breakthrough in 2019 and 20, and it came from product structure. So one of the authors was there when we proved this product structure, Cyril, and this is his favorite problem, I think. It looks to be one of his, sound like it's one of his favorite problems. And he, of course, immediately saw that this product structure can be helpful for his favorite program, and they made a breakthrough here with the 4/3. Okay, so what we did is we okay, so there's a whole table of past result. We managed to get the optimal result. Optimal meaning we managed to get 1 in front of the log n for the labeling of planar graphs, which of course based on for universal graphs means there is a universal graph that contains all planar graphs that has n plus something, n to the 1. So the size of universal graph is n to the 1 plus something, something small as the for the planar graph. So there are so that's up to lower order terms. This is the best we can hope. So let me tell you how we did this. All right, give you some idea how we did this. All right, so, oh yeah, by the way, the corollary of the, oh yes, so here's the corollary. Corollary first, this is that every planar graph is a subset, induced subset of, there is universal graph or n to the 1 plus little o 1 vertices. I already mentioned that. But there was another, so what did we actually prove? It goes back, again, it was using product structure theory. Okay, so what we actually prove is that if you have a family of graphs, such that every member of the family is a product of H and a path, and H has 3 with at most T, and T is some constant, then you have a labeling with this many bits, 1 times log n plus lower order term. That's what we proved. We didn't prove it directly on planar graphs. We really proved it on all the families where elements of a family are subset of some product, okay, of a product of some graph of 3 with T and a path. That implies that all these results as a corollary, that we got log n bound not just for planar graphs, but also all those that have the structure which is bounded genus, apex minor free, some non-minor closed families that we proved in the meantime, and so on. All right, but by the way, there is an open problem to mention here. We don't know how to do both, we can do click sums, but not apices, and we can do apices, but not click sums. This 2 log n is still the best for all proper minor closed families. Let me leave that. I mentioned this if I don't get, I'm going way slower than I thought, but surprise, surprise. Okay, so there is an open problem. I find very interesting one. For most of these applications that I mentioned, by the way, queue layouts, non-repetitive graph colorings, and so on, we got results using product structure and then using some ad hoc method. We come up with something else to extend it to all proper minor closed families. So we did manage to do it for other problems, but not for this one. And it's not for the lack of trying. So there, I think this is a nice problem. Can you improve 2? It's not even 4/3. 4/3 n also was not. So it's still at 2 log n for all proper minor closed families. All right, so how did we solve this? I'm gonna try to give you some idea of how we solve it for something much simpler, which is just product of 2 paths, okay? So a subgraph, in fact, induced subgraph. So I'm looking at graphs. Here's the family of graphs I'm looking at. I'm looking at induced subgraphs of product of 2 paths. And actually all the ideas are there. All the main ideas, everything that had to be solved comes up in this. And then you have to kind of do more ugly hammering and stuff to make it work when one of these things is not a path, but it's actually a graph of constant tree width. Okay, all right, so let's say, so the black vertices in the picture. So we have here, this is a product of 2 paths, one of length m and one of length h. And I want to label all n vertex induced subgraphs of that product. Okay, so in this case, the black graph is my induced subgraph. Okay, and unlike in my previous problem, I cannot take edge maximal things. I need to answer, is edge there or no? In fact, is even vertex there or not? So this is where the difficulty comes from. I can't just, apply to these, just say apply the tree width thing, and it's all the same in every row and column, and it works. Okay, so this is really, you're really looking at subgraphs. You have to work with subgraphs. Okay, all right. So what would be an obvious way to label this graph to be able to answer adjacency queries? All right, so the most obvious one is that for each of these vertices, you give it, so we have rows 1 to h, and we have columns 1 to m. So for each vertex, you give it a row, it's row I, and you give it a column. Okay, so, and then in that case, if you give 2 vertices, I have two vertices. All I have to check, because this is an induced subgraph, all I have to check are the 2 vertices in consecutive columns or in consecutive rows. Right? So if I have 2 vertices, in order to be adjacent, they either have to be in the same row and in consecutive columns. I have to check that. Or they have to be in the same column. And basically, just by checking rows and column, I can figure out if they're adjacent. If I could encode both rows and columns, okay, the names of the rows and columns. But that, again, that would be log of the number of bits would be log of number of rows plus log of number of columns. Well, both can be n or close to n or n over 2 or something like this. So we end up with 2 times log n with that type of scheme, and we don't even beat the other one. Okay, so here's what we do. Here's what the plan is. So what we don't need to know which row I'm in, which column I'm in. So given 2 vertices, I don't need to know this one is in row 10 and this one is in row 11. I just need to know are they consecutive rows or are they consecutive columns? So we need to be able to encode in a way that we are able to answer consecutiveness, okay, of the words. So that allows us to save a bit. So here's the three parts that every vertex in this. So if you look at the vertex that is actually in the graph, so here are the three parts that every vertex is going to have, okay? It's going to have a row label, okay? So it's going to have a label that corresponds to its row, all right? It doesn't mean it's its row number. It's just a label, and every vertex that is in the same, all the vertices that are in the same row, they get the same row label, okay? And I'm gonna do that by saving a bit. So what is this NI here? So we have a row 1. I'm gonna say, okay, in row 1, I have N1 vertices. In row 2, I have N2 vertices. Okay, so number of actual vertices in each row, I'm going to denote it by N of I, N subscript I. Okay, so we are going to have row labels that take this many bits, log n minus the log of the number of vertices in that row. We're going to save that many. So that means if I, for example, where does intuition come from? If you have lots of vertices there, I should use short label for that, for rows that have lots of vertices. Okay, this is going to be 1. So that means if I manage to do that, that means that for each row I saved log of ni bits, and that row has ni vertices, and so that row has ni vertices, and then the question is, how do you, in this particular case, this is really the graph induced by a row has a it's a forest of paths. Okay, so then you want to encode this. You want to encode each. We call it column label. This is graph induced by these columns, but it's really graph induced by a row GI. We're going to try to do that with NI labels. Okay, so imagine that we managed to do that. Okay, so I'm going to really, or you can even imagine that this is graph of 3 with H, and you apply bang, it has only NI vertices, and I can apply the result of that was known that uses log of NI bits. Okay, if that's all there was to it, we would be done, or at least here's what we can then do. If suppose we can do these two things, what can you then solve? You give me two, so let's say we graphs are labels like this, and I look at, so I have 2 vertices, I look at their row labels. If they are in the same row, then I look at their column. If they're in the same row, then I look at their column labels, and the column labels are going to tell me, are they consecutive on the column? If they're consecutive on the column, edge is there, this is induced graph. And so we would be done. So if they're really in the same, if the 2 vertices are in the same row, then we are done. Column label tells me, are they consecutive, or if you're using the hammer from bounded tree, they tell you in the bounded tree with graph, are they adjacent? All right. So if the 2 vertices in the same row, we are safe. All right. If the 2 vertices if the 2 vertices are not in 2 consecutive rows. So we look at we have 2 vertices, we look at the row label, and the row label tells me, remember, row labels can just tell me, are these 2 vertices in consecutive rows? And like this, it tells me, no, they're not in consecutive rows. Well, but then we know they're not adjacent. We say no immediately. Okay, but here's the problem. The problem is, if I have 2 vertices, I look at their rows and row labels, and row label tells me they're not in the same row, but they are consecutive on 2 consecutive rows. Then you say, okay, no problem. I'm going to go look at the column label, but column label of column label of this vertex here is based on the graph induced by row I. Column label of this on the top vertex here is based on the graph in the previous row. They're not related. Okay, at least you can blindly say apply a result on this row, apply a result on this row. You have to now figure out, are these two vertices adjacent? So that is the main difficulty about this for this problem. Well, in addition to the fact that I didn't even tell you any of these things, how do you do, for example, a row label that uses this many bits? Okay. So for that, we actually use, let me see, I have 5 more minutes. All right, let me just give you one idea. So here's, if you look what we're encoding, row label is just labeling, it's labeling 1, 2, 3, 4, 5, these are, so this is also like a path. We are labeling vertices of the path. Each graph induced by a row is also a path, or rather forest of the path. So what you end up solving much of the time is, at least for this subproblem, is given a forest of paths and what labeling you're going to use such that you tell me on this path are these vertices adjacent. Or other words, if it's a forest of path, I need to know, is my guy before me, is he or she there? Okay, so I need to do that type of query. Given a path, give me some nice labeling such that I can do that well, and such that you use this many bits for the row labels. Okay, so here's how you do it. You use binary search tree. So this is your path. This is a forest of path. For example, we have this path, then one vertex is missing, then we have this path. So each node on a path corresponds to a node in a binary search tree. So what's a binary search tree? Let me remind you, this is 1, 2, 3, 4, 5, 6. So here the root is 6. Everybody to the left are the vertices in the path with a smaller numbering. You number the vertices on the path from 1 to ni. And everybody to the right has a bigger label. Okay, so how do you label the vertices? So you build a search tree, binary search tree, on the numbering of the path. And what is the labeling that you use? Okay, so you basically, so let's say you want to know what's the label of this vertex. You look at the tree, and then you just label the path from the root to that vertex. So if you're going to the right, you know that by 1. So the label of this one would be 1, 1, 1. And so the label of this vertex would be 1, 1, 1. The label of this vertex would be 1, 1, 0. Okay. So that would be the labels of the vertices. So how many bits do you use? You use the depth of the tree. So if your tree is at all balanced, you are hopefully using log n bits. But here we want something a little bit stronger, which is this thing here. Okay, this is for the rows. And in addition to this thing that takes you, in addition to this signature, this we call a signature. So you label what is the path that you take to that vertex. So 1, 1, 0. In addition, you encode who is the predecessor on your path, on the path. Is your predecessor on the path there, or predecessor in the tree? So for example, here, for this vertex here, its signature is 1, 1, 1, 1, but we can put a specific label, let's say O. We always indicate O if the vertex before it's not there. If the vertex, so that was an easy case. You just indicate this vertex, its predecessor is not there. But let me give you a more interesting example. For example, this one here. This is probably the most common situation. let's say this one here. So we are looking at this vertex here. Its signature is 0, 1, 0. So that is the depth of the vertex. Signature takes the depth of the vertex, which can be log n. But you need to know the label of the predecessor, and you don't want to spend another log n. Okay, but your predecessor, you can, in this situation, when you don't have a left child in the binary search tree, you can always find your predecessor by going backwards in your label, and it has to be 0, 0, 0, 1. In this case, there's only 1 0. So if you have a label 0, 1, 0, 0, 0, you're going to find your predecessor by removing all the 0 and the first one. You're going to get the label of your predecessor. So just from the signature and a few bits of extra information, you can not only have a label, you can also work out the label of your predecessor. So if somebody gives you 2 labels of the vertices, you can figure out from your own label what is the label of my predecessor and check if the other vertex is that. And then you can say, if it's a predecessor, you say yes, we are adjacent, otherwise you say no. Okay. It's all right. So it's 5:30. I'm nowhere close to explaining this. All this to say, let me just say that each one of these rows and each one of these columns, you can use, because they're induced paths, you can use binary search trees. You can, in fact, use so-called weighted binary search trees, such that you achieve this. This is a known structure. To achieve this thing, that the vertices that have more, that the rows that have more vertices have shorter labels, you can achieve that by this weighted balanced binary search tree, which causes such a row, a label, to end up closer to the root. So then the label is short. So when you're using this binary search tree, you're using the weighted one to give you labels, like this. All right. So for all of this, to solve this thing, and this was just the beginning. To solve this thing, I'm not gonna give you any ideas, but it needs more than 1 trees for rows. It needs 2 techniques from data structures, which is fractional cascading, and basically dynamic binary search tree with working with insertions, deletions, and rebalancing. And I have to say we were lucky because we had Pat Moore in the group, who is absolutely spectacular data structure, who did magic that otherwise I really don't think would have been possible. So let me give credit where credit is due. None of this would happen without his. And actually it's not, let me mention that it's not, I don't think it's a surprise that actually the best bound for the trees where they got log n plus all 1 also is from the data structure crowd. So there's tons of data structures to achieve this result. Okay, so this is way too optimistic, my slides, but I will just end with an open problems, which I already mentioned, which is this compact encodings. Can we do them? Can we break 2 log n for proper minor closed families? Okay, I'll stop here.
Vida, thank you very much for a fascinating talk. So please, if anyone has questions, do ask. Maybe I can ask something. So actually, I had two questions. One was, so you've got the sort of tremendous stuff that has come out of these this strong product decomposition. Does everything come with algorithms as well? Is there always?
Yes. Pat has a paper as well, not only to compute these product structure. First of all, the question is how do you compute product structure? And then if you have a product structure, do you have an algorithm to solve a problem? And the answer is yes to both. And for computing product structure, I think there was obvious n to the 3 or squared bound that came from our paper. Obvious, I mean, once you work out but Pat has a paper, again, data structures, and he does it in n log n. So you can compute, well, at least for planar graphs, all these other things, I guess, assume that you're given, let's say if it's bounded genus graph, I believe you assume that you're given embedding on the surface. So yes, that's, that you can compute a product structure n log n, and all the other ones, yes, they have algorithms that, I don't know, with n to the some small constant, let's say.
Okay, very nice. My other question was just to ask whether you had anything more to say about these adjacency labelings or encodings. So both for the planar graphs, there's this lovely universal result with little o log n error term. Is there any hope to squinch that down?
Yes, this could be squished down. Probably, again, by my guess is with somebody really into data structures, that this is not, in fact, our little o of n, it's square root of log n. It's not log n. We get square root of log n from this rebalancing, from the rebalancing of this binary. Every k step, let's say, we have to rebalance, then we optimize for k, and gives square root of log n. My guess is this has to be improvable, but not by I don't know. You need some serious, even more serious data structures, I think, for that. And let me, by the way, mention, just for this universal graph, because I assume that people find this very interesting, as I did, that there is even now a stronger result by Gwen and Pat and Louis. They looked at one of when you start thinking about it, you ask yourself, okay, so you guys minimize the number of vertices. How many edges does this graph have? It's an induced graph, so it's not all the edges, but how many edges does this graph have? It's quadratic on this number of vertices. And I think the way we constructed it, it could be dense, the number of edges, but they modified, they have a whole paper about that. It's on archive. So they managed to get the number of edges, which is of the same order number of vertices. So also n, so it's induced universal graph with n to the 1 plus a little of 1 vertices, and also that many edges. So they improved that too.
And final question: do you believe 2 or 1?
I think it's 1. I don't know. We should be able to. I don't know. I believe it should be worked on. You mean for the minor closed families?
Yeah.
I believe it's better than 2, but who knows?
So, would anyone else like to ask a question? Okay, if not, then maybe this is a good point to pause the recording and have a big round of applause. So,